friends, we are with the last and 13th video in our Webots ROS2 tutorial series. So in this video, we will see the implementation of AR tag project. So if you have not looked at the 12th video, do have a look because that will give you idea of overall technology and overall project implementation. So we will not waste much of our time and start the implementation soon. After which we will thank our stakeholders and our friends without whom this video tutorial series was not possible. So let's start. So in this part, we look at enabling our camera and enabling our wheels of robot. So in this file, we have written this in Python. So we import RCL.py, we import Webots node and a twist message. First, let's quickly go through how we enable the wheels, and then we will look at the main part, which is how to enable the camera. So here in our class, we have these names in our proto. So my front left wheel is known as left underscore front underscore wheel. So I use this get motor function and get the handle to the left motor. Then I set the position to be infinity and velocity to be 0. So similarly, all four motors get their position to be infinity and velocity to be 0. After which we subscribe to command velocity. So some node will publish command velocity and this node will listen to command velocity and calculate the speed of left wheel and right wheel and publish it to the required wheels. So when I get a message in command vel, it goes to this callback function, which is here. So in this function, we define wheel gap, so the distance between two wheels, two front wheels, and wheel radius. So those of you who know differential calculations, this is the formula which includes linear direction velocity and angular z velocity, and we compute left speed and right speed. Then we clip the speed so that we don't get a very high or very low speed. Then we set the velocities to the respective wheels. So our front and rear left wheels get left speed and front and rear right wheel get right speed. So this is how we can translate our command velocity into real motion of wheels. So now the main part. So in this, you should note that usually we don't have Webots node here. If you are implementing some project, you will usually have their node, which is a implementation in ROS2. But here we are using Webots node. So these has many special features, like if I make a dictionary device config, I just need to write here sensor name, which is given in proto, and its value will be the parameters. So in this case, my camera name is camera underscore mid, and the topic name in which I want to publish my camera output is /camera, and my time steps is 16 milliseconds. So once you note down the list of all the sensors which you have in your proto, you just need to write one line, which is self.start device manager, and you give the dictionary as an input. Just by doing this, you will start getting messages on the topics which you have given. So this is a very good feature if you want to do advanced projects, and if you have many sensors, do take advantage of this implementation. And pretty much standard main, where we initialize ROS2, then we make object of our class and we spin the object. Once object is used, we destroy the node. So in this file, we will look at the actual pipeline which is implemented. We have some includes where we have a twist message which will be used by command velocity, which is our output. Here we have CV2, and we are using cv2.aruko as aruko in this project to detect our aruko tags. So we are using here CV bridge, which is a bridge between ROS and OpenCV. Here CV2 converts our ROS messages into images and images back to ROS messages. So we start with the node where we publish command velocity. This is actually expected because this is the missing part of puzzle. In last file we saw how we are using command vel and publishing it to robot where robot is moving. This file is responsible for taking in an image, processing it, and publishing a command velocity according to the processed image. So we publish command vel. We have bunch of constants, and here you see we subscribe our image. So in ROS2, whenever Webots publish image at a topic camera, we get an image camera/raw image. And for understanding our pipeline, we are also publishing the processed image which can be viewed. So here let's go to the pipeline. This file will spawn once you get an image in your camera/image raw topic. So when you get a message on this topic, it will go to callback. So I should come here in callback. First of all, we will convert the coming message into a frame which CV can understand. So in message, we will also get height, width, and here note that as we have an ideal image, so our camera matrix is pretty linear. So here camera matrix is the accountability of your camera. So if you have a camera which has issues with focus or which has center offset, you need to change these parameters. If you want to learn more about camera and camera matrix, do go to CV2 documentation. It is documented in a great fashion. So here we are using camera matrix and distortion coefficient. So our camera is ideal, so we don't need any distortion. So it is 0, 0, 0, 0. So first of all, in our pipeline, we convert our frame image into grayscale. So now we will be processing the gray image. Then we load the dictionary of Aruko tags. So here Aruko dictionary, which is Aruko dict, is nothing but it's a dictionary of 250 Aruko tags, which are 5 pixel by 5 pixel. These are standard dictionaries which are usually used by computer vision people in order for pipeline to detect the ID of that Aruko tag. We also have Aruko parameters, which we are getting it from this function. So first of all, we detect the marker. So we have a function named detect markers in Aruko tag, where we give our grayscale image. we provide the dictionary of all the tags so that this function can choose from those tags which is nearest to the shown tag. Then it takes in parameters. It takes in camera matrix, which is ideal in our case, which is 0, 0, height by 2 and width by 2. Distortion matrix, and that's it. So this will give me output of number of tags where I will get a list of IDs and 4 corners of those tags. Once I get these tags, I will run through all the tags. So I will go through one by one. So when I take one tag, I estimate position of single marker where I take in corners of those tag and I give the correct size of tag. So estimate pose single marker function uses the correct size of tag. This is really useful when you want to know the distance between your camera and the real image. So here we are giving corners, we are giving the actual size of our Aruko tag, we are giving our camera matrix and distortion matrix. After giving this, we will get a rotation and translation from our camera frame. This is exactly the pose which we want. So we will draw a frame on our markers and we will draw axis on our image. So we will draw a small box on our image where we see the Aruko tag, and also we will draw axis on our image. So after doing that, we have implemented a goal reach criteria where you see that our robot stops when it reaches near the AR tag. So what we are implementing here is if the height of my image AR tag is greater than a threshold, we consider that we have reached the goal, and else it will continue to propagate towards the goal. So our threshold here is 0.4, which is 40%. So this says that if my AR tag occupies more than 40% of my image frame, that means we have reached the goal. So these are the conditions where we have reached the goal. And finally, when we have an image which is marked with a box around AR tag and also the transform, we publish the image to the topic processed image. And again we will need to convert our CV2 image into the image message. So here CV2 bridge comes handy. And once we publish this is where we will see the frames. And on the other hand, we, according to the translation of marker in our image, we command our robot. So we go to correction module function. In this function, we set the linear x as constant speed and we set the correction into the translation of x. That means here we are setting the rotation according to the distance of AR tag off from our camera frame. So here we are implementing a bang bang controller where it will make sure that the AR tag remains in the center of our frame. We have two conditions here. So if the goal is reached, we send everything to be 0, 0, which is expected. And if we don't see AR tag, we search. This means we look around, as you must have seen in the implementation where robot rotates around itself when it doesn't see an AR tag, and once it starts seeing an AR tag, it goes towards the AR tag. Once we get the command velocity, we publish it through this message. So now you know this file is used to take an image, process it and send the command velocity. So after looking at the implementation, now let's look at how to make these files work in ROS2 infrastructure. If you guys have followed full series, you must be feeling that Setup.py is very easy affair. So here, this file is responsible for what gets built. So here it takes in all the files, like it takes in our launch files, our world, also it takes in our proto which we are using. It takes in the textures, and we need to specify our file names in order to be used in our launch file. So if you write a Python script and if you want to launch it through launch file, you must register it here. So in our case, we have commander.py which implements the computer vision pipeline. So you see here we have commander.py. You don't need to write .py, it takes it by itself. And we need to write Webots ROS2 tutorial.commander because in our package we have a Webots ROS2 folder. So if you see, this is our package. In our package we have a Webots ROS2 folder, and then we have commander.py. So this Webots ROS2 tutorial signifies Webots ROS2 tutorial folder. We have also added robot enable here, which is also in Webots ROS2 tutorial folder. So if you had these two lines in your entry point, and we made proto with the camera, so we have its name here, and this is the world which we are using, which is custom robot AR tag, and this is the name of launch file, which is AR detection launch. So this is all about setup.py. Let's look at the launch file which we are using. It's a very easy and pretty forward launch file where we get package directory. So these are the standard functions of ROS2 where you get package directory. In our case, we are using Webots ROS2 tutorial package. We have a core package because we see many functionalities in our Python files which are directly used or implemented in this core. After this, we make a Webots node where this Webots is responsible for spawning our world. So we use robot launch.py, which is a standard Python file given by Webots to us, and there are many arguments to it, but we are using package as Webots ROS2 tutorial, executable as camera enable. This is the node which we made in order to enable camera and wheels, and the world parameter which we are using is package directory /world /custom artag.wbt. So again, we don't need to go in depth, but I will show it to you that in my package, when I open this, we need to go to, I'll close this for a second. Yeah, so this package directory signifies Webots ROS2 tutorial /world signifies the world folder, and when we open world folder we have custom artag.wbt, which is this. So this is the WBT which we are using in order to implement this project. And on the other hand, we have image commander, which is just a bare node where it's in package Webots ROS2 tutorial. Its executable name is commander, and we are making the node name to be same as executable name, which is commander. So I have these two things where I have Webots launching and a node which is our computer vision pipeline. So I need to send them to launch description. So I send Webots, image commander. So this is how you write your launch file in ROS2. So here you must be seeing that we can implement many intricate logics because it is written in Python. So this is all about the package and how we can run our project. So in this section, after doing this coding, now it's time to showcast the results. So let's build the project. So you need to come in your directory where you will have your source folder. My project is already built, but if you want to build the project, you need to type colcon build, and when you hit on enter, it will make the project. Once your project is ready, you will need to launch your launch file. Before doing this, we will need to source the directory. So source install setup.bash. This source is important because now our ROS system will know that there are some launch files and Python files in this directory. So now if I do ROS2 launch Webots ROS2 tutorial, so autocomplete comes handy in such case, and if I click AR and hit on tab, it will autocomplete the launch file name. If I hit on enter, so you see our robot is searching for the AR tag. Yeah, it found the AR tag. Let's make our robot's life a bit difficult. Let's take it here. Let's not show it the AR tag. Till that time, let's do one thing. Let us again source install setup.bash, and here we will do the processed image. So if I do ROS2 run trqt image viewer, so rqt image viewer. So if I hit on this thing, I can see images which are different topics are seeing. So we have two topics, which is raw image and processed image, which are publishing the image topics. So if I minimize this for a second, now you will see that when our robot sees AR tag, it will show us the detection here. So this is our basic image, and you see here our robot is detecting the AR tag, which is the green boundary, and it is also giving its translation from our camera frame. So for a second, if I click on shift and if I move the robot, you will see the translation moving. And also in code, we saw that if our robot occupies more than 40% of the AR tag, it stops. So we will see here when this AR tag is becoming bigger as robot is approaching the tag. So let's see, when it stops, we will see a message of, so it stopped and we are getting a message reached the goal. That is exactly the goal which we had for this project. So this was all about this project.